To our next speaker, Christina Mesropian, Vice President of AI and Machine Learning at Numeria Future Trends, where she leads strategic initiatives in the next generation computational technologies. In her talk, From Pixel to Proof, she will dive into how AI-powered digital product passports can create verifiable, tag-free links between physical objects and their digital identities. Please welcome on stage Christina Mesropian. Thank you.
Good afternoon. First, I would like to thank the organizers for invitation to this really exciting and very interesting symposium. I'm really honored to be here. And of course, the comment, it's very difficult to give talk after Alex, after such a deep and encyclopedic talk, so I'll just try to do my best. Artificial intelligence redefines how we process information, but it also changes how we define trust itself. For many centuries, we were relying on the human witnesses, on the institutional seals, on the visible marks to establish the authenticity. But in our digital world, where everything from the art to identity can be replicated, the question becomes not how to connect the data, but how to prove what is real. And that becomes basically one of the main questions of the modern digital economy. So in this talk, I will try to show how artificial intelligence can serve as a bridge between physical and digital worlds, how it transforms the verification of the origin, integrity, and history of the objects that we produce, buy, and value. So going back to the trust. And trust is a word that was actually mentioned many times at the symposium in this last 3 days. And I believe one of the speakers at the first day during the conference climate section mentioned that trust should be built. And I really like that statement because it really kind of echoed the sentiment of this talk. Trust should be built. Trust in reality is the invisible infrastructure of trade. Going back to the Silk Road that Alex was mentioning in his talk, some 2,000 years ago, the merchants that were crossing Asia, they didn't only have to navigate the dangers of the distance, the danger, but they also have to deal with the doubt about the authenticity of the goods they were transferring, whether that the silks or spices or some ceramic plates. How would they know that the goods were really the authentic after they passed through so many hands? So what they resorted to is the use of the physical proofs. Wax seals, color-coded nuts, some stamped clay tablets. In reality, each of these kind of methods was a very primitive proof of identity, which was tied directly to the object itself. Now, moving to the 1974, when the little black bars on the back of the Wrigley chewing gums were scanned at a department store. And that's basically started the age of machine-readable commerce, when digital systems could just keep the information about object in itself. For 50 years, barcodes, the QR codes, the RFID tags were very successful in providing and becoming these anchors of identity. However, this methodology works really well for the simpler and linear economy. In our global and circular economy, when materials move across borders, they are being refurbished, repaired, resold, recycled. We need stronger solutions. We need verification that can be verifiable, intrinsic, and persistent. So how do we fill this gap between the physical world, between the products, between the digital world, between the data sets and apps? We need the verification proofs that will rely on the intrinsic properties of this object. So we need something that will be able to tie up between the pixels and the proofs. And this is where the digital product passports or DPPs come into the picture. They're promising, they're basically creating this one of the most promising frameworks for tying the trust directly to the living record of the object itself. So they can be carrying the information about key data on the products from where it was originated, what materials it was built, what kind of ownership history is behind that particular object, and also as well the information on the environmental impact of that object. And that's the reason why it's supported by the major industries, and it is one of these regulatory initiatives. Digital product passports allow us to create this link between this object by itself in a way that avoids having this paperwork related to that. So it's defined by a clear scope and governed by agreed rules for the data management and access. By itself, the technology is new, but the concept obviously isn't. In 17th century, a very famous violin maker in Cremona, Antonio Stradivari, was keeping very detailed records in his workshop about every violin that he was creating. Every instrument had detailed information about wood used, the recipe for the varnish, the names of the people that that were acquiring the instrument. Some 300 years later, these ledgers are still being used to authenticate the instruments that were bought by Stradivarius. So now we're using basically the similar principles, but it's pushed across global infrastructure now. Now, instead of the ledgers and signatures, we're using encrypted digital records that are accessible on the blockchain and augmented by artificial intelligence for verification purposes. So now we have the digital product passports. We have the digital records of the object. But the next question comes in: how we can be sure, how we can guarantee that this particular digital record is representing this particular object? And historically, we were using the tag-based external identifiers, such as the QR codes, the serial numbers, RFIDs, holograms, and that work pretty well. They are very convenient, they are easy to attach. However, they are also easy to remove. They are easy to copy, they are easy to fake, they are easy to create fraud with them. So the new world in this development is obviously the intrinsic fingerprint-based signatures, when the object's own physical texture and structure becomes important. So every physical object, no matter how tiny, has these unique signatures that are very, very identifiable. For example, if we look at this corner here, there is a brush stroke on the painting, which is absolutely unique. You look at the right corner, there is a gold material there from the jewelry piece. It has the etchings, which are very unique for the signature. Again, some leather from the piece of leather that's used for making some luxury handbags, let's say, again has a very unique signature. So all of these representations basically create the basis for the intrinsic fingerprint of the object. And that allows us to go from the physical object to the camera with the scanner, through the artificial intelligence verification and digital passport. And this is where artificial intelligence becomes important, because analyzing and quantifying this kind of identifying these signatures is not possible to do with the human eyes, so artificial intelligence, that's where it becomes the trust of engine. So when we're taking the image, photo image of the object, basically, we are recording how this object reflects and scatters light, right? This is just physical trace of the object's material and structure. And for quite some time, this is where the process would stop. The camera was taking the image, the humans were making judgment, passing judgments. Now, artificial intelligence is changing this dynamic completely. It allows us it not only looks at the object, but it tries to focus on what makes the object what it is. So basically, with the artificial intelligence now, we can look at the signatures that are, it can learn from the object by itself. It can learn from the structure. The small variations in color and texture, they represent the structure of this material. With artificial intelligence, now we can basically connect the shapes. It doesn't only see the pixel by pixel, it sees the image by itself. So the variations in texture are reflecting the shape. The reflections on that image are reflecting the curvature, and irregularities are becoming the signals of the uniqueness. So by using this, it allows us basically to create this perception and converts it into the quantifiable data. And each object is basically producing this unique visual DNA. So in this case, by recording this, by analyzing this, we are kind of creating an image of that DNA. So the verification process becomes really inherent. It's not attached to anything. So the product starts speaking for itself. Now, to understand how, to appreciate how we're moving now in this process of AI use for the image verification, it's important to distinguish between processes of recognition and verification. In the traditional AI vision systems, AI was designed to label the objects, to ask the question, this is the chair, this is the bottle, and that's the questions that were asked. For the verification purposes, we are not concerned with the question what it is, we're concerned with the question, is this object is the same one we saw before? So for these particular purposes, for the technical purposes, they were concerned with the concept of embeddings, which are these high-dimensional numeric vectors that encode the image visual structure, its texture, geometry, into a compact mathematical representation that preserves the similarity relationship. This way, when we are looking at the object, we don't only see just pixels. We see the reflection of the whole structure. We see how the embedding can translate the information across the border. So if we're looking at the images of the same, let's say, product that was taken with two different cameras, and if we see the embeddings of both of these materials living close into this learned feature space, after they pass the cosine of similarity, passing the certain threshold, we can say that these embeddings basically represent the same object, and our matcher will produce the positive output for this recognition. So this way, the similarity in this feature space that we create with embeddings, that allows us to give this verification of the verified match. So our, again, perception becomes proof, and it creates this kind of, we are moving in the space of the geometry of the trust. Now, the AI image matching went through dramatic progress, and some of the very advanced methods today used for that are called the detector-free image matching with AI-based models. So basically, traditional image matching systems were used by selecting a few key points. And key points were representations of the unique structure of the object. For example, edge, corners, some blobs of paint. So it was using these unique key points and then comparing the key points across various views. With the detector-free image matching, we are not looking at the pixels. We are looking at the image as a dense representation of the feature field. And that allows us to avoid situations like with traditional systems, because all the traditional systems were really efficient, but they will break down when you see the change in the light conditions or in the perspective. They wouldn't simply work when the object wouldn't have some defined edges or structure. So by looking at the object by itself through complete image, when complete image comes into the representation, you're avoiding situation where you're losing information. You can handle regions with the low density. You can handle regions that have like light reflected. So it's much more stable and useful for the real world situations. So this is the detector-based models we're using. From the technical point of view, we can say that each image is represented as a feature tensor in the spatial dimension, so it reflects the local characteristics as well as the spatial relationships. Then we're using one of the really good hybrid models now in the market for the image matching is so-called ROMA matcher that is built on top of this Dino V2 feature space. So by basically creating these local vectors and then comparing the values for this with the ROMA matcher between these calculations, we are computing matcher using this cross-attention method. And then we feed it all into this so-called the aggregation with the transformer embedding heads. That's for people in the audience who are experts in this, and that all results in the production of the embeddings that we were talking about. So all these layers of these different stages of the processes, they bring us to the embeddings that we were casting before. Because embeddings, basically, they are the digital fingerprint of each object. By creating this embedding, we are able to index it, store it into the database, and have really quick retrieval, if necessary, across millions of images. So that allows us to basically have really functional, really scalable systems across many different objects. So now moving into the that's a very interesting principle. It's a very interesting technology. So how do we want to apply it in the real world? And this I'm going to steal from the idea from Professor Pentland, but then Professor Novoselov stole it first. So it's always good to operate in the space when there are gaps between different fields. So we will try to use this kind of technology in computer vision for the art. And of course, art is also a very interesting direction to take this kind of developments. We're in Abu Dhabi. You can see this amazing cultural district, rising in front of our eyes with the Louvre Abu Dhabi, with 2 new museums coming up. Large galleries are popping up all the time. New art fairs are coming. So that's a very interesting, vibrant scheme. So it's interesting to try to apply and check what's the purpose of this test. To test how reliably the small localized image regions or visual fingerprints can identify the artworks. And what you can see here is a setup, actually, that we were using. This is flatted air is a painting, as you can see, under the digital microscope. And that's connected to the image on the laptop, which shows exactly that. That's a visual fingerprint. So by using this method, we are creating, it's non-invasive, it's not embedding anything in the art object. It just takes the image of certain space on your art object. It can be painting, it can be modern photograph, it can be sculpture, it can be metal artwork, it can be anything. But we're just showing here it's in application to the artwork. So we're taking this fingerprint. Now, what we're trying to do, this fingerprint is going to be stored on the blockchain, but I'm not going to talk about this now because I want to talk about the image matching part of that. So we're taking this image and we're storing it as a fingerprint. And then we're going to test it with the probe videos. Obviously, we have some setup of the real fingerprints that we took from real objects, real art objects. And that's a very good sample for our experimental setup. But we also need a setup to verify how reliable this methodology is going to be under very different light conditions, aging of these objects under some angles that are not controllable. So in addition to the real life, real probes that we took with the real handheld cameras or digital microscope, we also generate some synthetic data set. And for synthetic data set, we, in addition to all the real images that we have from the cameras and microscope, we also created synthetic fingerprints from free access from the museum online imagery, where for each particular art object, we create some fingerprints. And here in the right corner, you actually see how we can do that. We're taking this is the image part of the fragment of the artwork, and you can go and basically zero on some particular interesting visual corners that have some interesting features to that are easier to fingerprint. You can create few fingerprints across the artwork and store it. So we ended up with this data set of the fingerprints, both from the high-resolution artwork images in the museums, that's what we call our synthetic data, as well as the real images from the real artwork, and props, our videos. So synthetic short videos that simulate control conditions, we use them to generate the changes in lighting, in aging, different styles of aging. We use scratches, fading, stains. Obviously, we're not going to do that to real art, but we can go completely wild when it comes to the static prop videos. And with the real hand catchers, you can check the natural variability. Like my hands are very shaky, so when I take photographs of this or videos of this object, that introduces quite some shift in the angle. So that gives you some real possibility to test the robustness of the algorithm. So each fingerprint is matched against the prop video, and then we are using the same AI-based matcher. And then we obviously aggregate these values across all these results and compute the unified metrics such as the area under the curve, the precision, recall, so on and so forth. And the results that we obtained actually look really, I would say, pretty good. They show really excellent discrimination for people who are like to look at the numbers and compare how this model works. They show that they have excellent discrimination ability. After you are tuning the thresholds where you accept the match by itself, we basically don't have any false positive results, which is excellent. You don't want to identify something as a real object that you have the digital record, and instead of that, verify some fake instead of that. So that's very important for these purposes. We have good values which demonstrate the consistent detection of genuine matches. Also shows very balanced performance. And obviously, also for our synthetic data set that creates variations in the aging for the props and so on and so forth, we see very kind of stable representation. We see only 3 to 4% degradation in the quality of the matches when we are using this really severely damaged synthetic prop videos. So here I'll just put this is basically a real-world application. That's what we do at the Numerian Future Trends. This is, we are producing the biometric level digital product passport for artworks, for collections. We can deal with very different cultural objects, with the items of the memorabilia, with the royal collections, with the objects from the cultural heritage. Obviously, it's very important now to preserve all these objects. That's the fingerprinting. Again, as I said, it's absolutely non-invasive methodology. The scanning and captures the unique structure of your artwork. It creates this immutable digital product passports are created there on the blockchains, the record of the identity and the provenance. There is obviously corresponding to the private collector dashboard. We worked with cultural foundations, with the private collectors, with large galleries, with some modern photography art fairs. Especially for photography, that's actually a very, very big problem, because once you end up in the business of the limited edition photography, how do you prove that somebody just didn't photograph it, print it as beautiful, super fake, and post it on the wall instead of claiming that to be the artwork you are supposed? Obviously, that's also a very big interest for the living artists, because that allows them to track the provenance, to track the history of their artwork they create. Okay, sorry, yes. So what are the takeaways and outlook from this kind of methodology? By itself, obviously, methodology is not providing only just this nice kind of elegant-looking solution. and or the technical merit. It has incredible potential. It has the significance in what it allows to enable. If every verified object can be linked to the digital record, then suddenly the authenticity becomes really accessible and measurable property. It can allow, if you are talking about the supply chains, it can allow the manufacturer to prove that he is sourcing the materials he is using are from ethical sourcing. It allows the customer to verify the origin and identity of the products they are buying. It allows the recycler to trace the materials that are being used that he's going to recycle. So that creates this chain, this trust kind of verification chain across different industries and makes it much more accessible. It makes this ability to prove, to verify the identification as a built-in feature of the economy and not just a wish for transparency. And obviously, what are the next steps? As I showed you a nice, beautiful application of this methodology to the world of art. But obviously, the absolutely obvious applications are for supply chains, for pharmaceuticals, for the materials, for the logistics companies that are transferring objects from one place to another. How do you know that your objects were not switched in between? So this AI-powered application of the image verification allows to create really fast, scalable, data-driven system that's going to work on all kinds of levels. And obviously, if we're being a little bit optimistic here and talking applications in future, the next step probably is to create this kind of verification system that would be interoperable on different levels. And you can have these digital records that are, being used by whatever the requirements of government policies, like European Union is pushing now. These passports can be used for provenance, for tracking, for collectors, for the manufacturers, on all tiny steps of our society. So next step, as I said, we're moving from recognition to verification, from pixels to proof. Let's try to see if it would be possible to create interoperable trust infrastructure across various industries. That's it. Thank you.
Thank you so much. Any questions from the audience? Said?
I just have one question. For your digital passport or the digital fingerprint that you have, I think for the digital passport you're talking about, or the digital finger, there will be a need for a standardization across all the different countries or the organization. And have you put any thought about that one? And also, with that, I don't know if the digital blockchain will solve, maybe that would require a central authority for the verification process to be, the protocol itself to be unified.
Okay, so in this case, you're talking about future developments or the current implementation of the technology? Because at the current implementation, we don't need, this exists on our platform. So that exists basically between the customers who use an access to this platform. They have an access. Let's say you have an artwork. You want to sell it. The access to the information to this digital passport will be passed to the next owner of the object. And obviously, this information is also secured. So there are some requirements how it's, if in the future, there will be additional government requirements to that. And that's what I think you mean when you were saying about standardification, right?
Yeah. What I meant, for example, is when you talked about the painting, you took a sample of certain areas of the paint. That requires standards, so it has to be in this square and that square, and the verification should be done in that way.
We're dealing with this issue because one thing is, and let's talk a little bit about potential super fakes and people being paranoid. So when we are taking the fingerprint by itself is not visible to anyone. So the way the fingerprint is taken it's being stored in our system, but it's not visible to other people. There is indication, for example, of approximate area where it's been taken. So when a customer comes in and brings it for verification, when they're scanning for the video, you can take an approximate area, but you don't know exactly where, exactly like the pinpoint of the fingerprint position. That's why we're using videos, not image-to-image comparison, which would be slightly easier, right? So this information is stored, there are indications there, but there are no like coordinate prescription. Also with paintings, it's easy. You are dealing with this, yes, two-dimensional. When it comes to, let's say, sculptures or some more three-dimensional objects, that becomes a little bit more difficult. Obviously, for our system, we have the standardifications requirements. There are. But if we're moving in the future, yes, then I can see how potentially, if, for example, dealing with the supply chains, obviously it is very rigorous and well-defined and, super standardized industrial process. With the art, you can be a little bit more flexible.
Thank you.
Thank you, Christina. Our next speaker is, sorry.